There is a moment that happens in encounters between humans and bald eagles that most people who have experienced it struggle to describe accurately afterward. It is not fear exactly, though fear is usually present. It is something closer to the sensation of being categorized, of being assessed by a system of perception so different from your own, and so much more acute in certain dimensions that the animal looking at you is not seeing what you think it is seeing. It is not seeing a person in the way that another person would see a person. It is seeing something else, something it has its own framework for. And the discomfort that follows that realization, when it comes, is not about the eagle's talons, or its wingspan, or its reputation as a symbol of national power. It is about the recognition that you have been perceived by something that perceives the world in a way you cannot access, and that what it found when it looked at you may not have been reassuring from its perspective either. This video is about what a bald eagle actually sees when it looks at you, not metaphorically, literally. The optics, the neurology, the perceptual architecture of one of the most visually capable animals that has ever existed on this planet. And why, when you understand what that architecture does, and how it works, and what it was built by millions of years of evolution to accomplish, the answer is genuinely unsettling in a way that goes beyond the standard wildlife documentary framing of eagles as majestic and powerful and impressive. The unsettling part is not what the eagle can see. The unsettling part is what it does with what it sees, what it knows from looking at you, what information it extracts from the image of a human being that the human being has no idea it is broadcasting. Before we go further, if you find this kind of deep, careful examination of animal perception and predator biology interesting, subscribe now, because there is a great deal more where this is going. Start with the basic structure of the problem. Human vision is, by the standards of the animal kingdom, mediocre. It is not the worst vision possessed by a vertebrate, but it is not close to the best. Humans have two eyes positioned at the front of the head, which provides good depth perception and binocular overlap, useful for the kind of precision manipulation tasks and social interaction that dominated human evolutionary history. Human visual acuity, the ability to resolve fine spatial detail, is measured at approximately 20/20 under ideal conditions, which means a person with normal vision can resolve a standardized optometric target at 20 feet that a theoretical baseline observer could resolve at 20 feet. This is the definition of average, not exceptional, not even notably good by the standards of vertebrate visual systems. The cells responsible for fine detail vision in the human retina, the cone photoreceptors concentrated in a small central region called the fovea, are packed at a density of approximately 200,000 per square millimeter at the center of the fovea. This density is what produces the approximately 20/20 acuity that humans take for granted as the baseline for normal sight. A bald eagle's retina contains approximately 1 million cone photoreceptors per square millimeter in the region of highest density. This is not a small difference. It is not the kind of difference that produces a modest improvement in the same basic capability. It is a difference of a factor of 5 in the raw cellular density that underlies the ability to resolve spatial detail. And that difference, when expressed in terms of behavioral visual performance, produces a system so far beyond human capability that direct comparison begins to strain the utility of the comparison itself. The estimated visual acuity of a bald eagle is approximately 20/4 or 25 under optimal conditions, depending on the method of estimation and the specific individual. What this means in practice is that a bald eagle can resolve detail at 100 feet that a human with normal vision would need to be 20 feet away to resolve. Or, to frame it differently, an eagle can see from the top of a telephone pole, approximately 40 feet off the ground, a mouse moving through grass at a lateral distance of roughly 2 miles. not 200 yards, 2 miles. This number requires a moment of attention because it is one of those biological facts that sounds like an exaggeration but is supported by the structural evidence, by independent estimation methods, and by behavioral observation in field conditions. The 2-mile mouse detection figure is not the eagle looking for a mouse. It is not the eagle aware that a mouse might be somewhere in a 2-mile radius. It is the eagle's visual system registering the specific movement signature of a small rodent moving through grass cover at a distance that, for a human being, would make the grass itself invisible as individual blades and the mouse as invisible as a molecule. The eagle is not using this capability all the time. Visual attention is a limited resource even in animals with extraordinary hardware. But the hardware exists. The capability is there. And when it is applied to the image of a human being standing in a field or on a riverbank or looking up at a nest site, it is extracting information from that image at a resolution that the human has no conceptual equivalent for. But acuity is only one dimension of the bald eagle's visual system, and in some ways, it is not the most interesting one. To get to the more interesting dimensions, you have to understand something about the structure of the eagle's retina that does not have a direct human analog. Human eyes have one fovea each, one region of maximum cone density per eye, one region where the finest detail resolution is concentrated, one point in the visual field where the neural resources for high-resolution processing are deployed most intensively. Eagles have 2 foveae per eye, 2 distinct regions of elevated cone density with different optical properties and different positions in the visual field, each serving a different behavioral function. The first fovea in the eagle's eye is called the central fovea. It is located at the center of the retina and handles the kind of fine detail, high acuity vision that the single human fovea also handles. This is the system that detects the mouse at 2 miles. The second fovea is called the temporal fovea, and it is located toward the outer edge of the retina in a position that, in terms of the visual field it samples, corresponds roughly to the region of the eagle's field of view that includes the area to the front and slightly below. The temporal fovea is not specialized for the extreme long-range detection that the central fovea provides. It is specialized for something different, and arguably more unsettling from the human perspective. It is specialized for close-range binocular processing and for the rapid detection of movement in the forward visual field. It is the system the eagle uses when it is close to something, when it is evaluating something at a range where the central fovea's long-distance specialization is not the relevant tool. When a bald eagle is looking directly at you, it is potentially using both foveal systems simultaneously to build a composite image that integrates long-range structural detail from the central fovea with close-range binocular depth and movement information from the temporal fovea, producing a perceptual representation of your body and your behavior that has a resolution and a richness of information content that a human being looking at another human being does not approach. The eagle is not just seeing your shape, it is seeing the individual features of your face at a resolution that would allow it to distinguish you from another person of similar size and clothing at a distance that, for you, makes human faces blur into undifferentiated skin-colored ovals. It is seeing the texture of your clothing and the specific movement pattern of your gait and the subtle behavioral signals that your body broadcasts continuously without your awareness. It is seeing your breathing rate, registered as the movement of your chest and shoulders. It is seeing the direction and speed of your eye movements, potentially at close range, as a behavioral cue. It is building a profile of you from the image of you that contains information you did not know you were transmitting. The color vision dimension of this picture compounds the unsettling quality of the assessment in a specific way. Humans are trichromats, meaning human cone photoreceptors come in 3 varieties tuned to different ranges of the electromagnetic spectrum: roughly corresponding to long wavelengths we perceive as red, medium wavelengths we perceive as green, and short wavelengths we perceive as blue. The color perception humans experience is produced by comparing the outputs of these three channel types and constructing a subjective color experience from the ratios. This is a reasonable color vision system. It allows humans to distinguish a very large number of color combinations and to use color as a cue for object identification, emotional state reading in other humans, and a range of other behavioral tasks. Eagles are tetrachromats. Their cone photoreceptors come in 4 varieties rather than 3, with the 4th variety extending sensitivity into the near ultraviolet range of the spectrum, wavelengths that human photoreceptors do not respond to at all, and that human consciousness therefore has no representation of. This means that the world as an eagle sees it contains colors that the human visual system cannot perceive, process, or imagine. Not colors that are hard to distinguish, not colors at the extreme edges of human color perception, colors that are entirely outside the range of human color experience, that exist in a part of the spectrum that human eyes are simply not built to register. When the eagle looks at you, it is looking at you in a color space that has a 4th dimension you are unaware of. The visual signals your body broadcasts in the ultraviolet are not signals you can manage or suppress or be aware of, because you have no sensory access to that range of the spectrum. The coloration of your skin, your eyes, your hair, the fabrics of your clothing, all of these have UV signatures that the eagle is reading and that you have no visibility into whatsoever. This matters for a specific reason that goes beyond the aesthetics of the visual experience. Ultraviolet reflectance is biologically informative in ways that visible light reflectance often is not. In many species, UV signals encode health status, physiological state, and behavioral disposition in ways that have been selected for precisely because they exploit communication channels not accessible to certain observers. The UV signatures of human skin and tissue are not signals that evolved for eagle consumption. They are not designed messages, but they are signals nonetheless. And an animal whose visual system can read them is extracting information about your physiological state from them, whether or not that information was intended for transmission. An eagle, looking at a human being, is looking at a UV-rich signal landscape that the human is broadcasting unknowingly. And some of what that signal landscape encodes, health, stress, physiological arousal, is information that a predator's perceptual system has been selected over deep evolutionary time to find behaviorally relevant. The flicker fusion rate of eagle vision adds a temporal dimension to this perceptual gap that is less discussed, but equally striking. Flicker fusion rate is the frequency at which a repeating visual stimulus, an alternating pattern of light and dark, a flickering source, a rotating object, appears to merge into a continuous image rather than registering as separate discrete events. It is a measure of the temporal resolution of the visual system, the speed at which the eye and brain can process successive visual frames and register them as distinct rather than blended. Human flicker fusion rate is approximately 60 cycles per second, under well-lit conditions. This is why cinema at 24 frames per second looks like continuous motion to a human observer. The human visual system is not fast enough to resolve the gaps between frames, and the result is the perceptual illusion of smooth movement. A bald eagle's flicker fusion rate has been estimated at approximately 130 cycles per second and possibly higher under high illumination conditions. This means an eagle is processing visual information at roughly double the temporal resolution of a human eye. It is seeing twice as many distinct moments in a given interval of time. Movement that is smooth and continuous to a human observer is, to an eagle, a high-resolution sequence of distinct positions. The trajectory of a moving object, a fish breaking the surface, a rabbit changing direction, a human hand reaching into a bag, is being tracked by the eagle's visual system at a temporal granularity that allows the extraction of velocity, acceleration, and directional intention from motion data that a human eye would process as a single blurred event. The practical consequence of this temporal resolution in the context of an eagle looking at a human being is that the eagle is reading your movements at a level of detail that allows behavioral inference. The way your weight shifts before you take a step, the direction your arm begins to move before the movement is complete enough to register its intention on a less temporally acute observer, the micro-expressions of muscular tension and relaxation that precede gross motor actions. An eagle watching a human being is watching a behavioral sequence unfold in slow motion relative to its own perceptual experience, extracting information about your likely next action from cues that precede the action itself. It knows, with a lead time that is neurologically meaningful, what you are about to do, before you do it. This is the same capability that makes eagles extraordinary hunters of fast, evasive prey. It is the same temporal resolution that allows a bald eagle to intercept a sockeye salmon executing a directional change at the surface. Applied to a human being, it produces a level of behavioral reading that is entirely one-directional. The eagle is reading you, and you are not reading it, not at anywhere near the same resolution. The depth perception architecture of the eagle's visual system is built differently from the human version, in ways that compound this asymmetry. Human binocular depth perception is effective within a range of roughly 30 meters or so for fine depth discrimination, with coarser distance estimation extending somewhat further through motion parallax and other monocular depth cues. The eagle's binocular visual field, the region where both eyes overlap and where binocular depth processing is available, is narrower than the human binocular field because of the lateral position of the eagle's eyes on its head. But within that binocular field, the depth resolution is extraordinary, and crucially, the combination of the central fovea's long-range acuity with the temporal fovea's close-range binocular processing gives the eagle a functional depth sensing system that operates at two different scales simultaneously. Long-range, precise enough to judge the depth position of a fish below a water surface from a height of 100 feet. Close-range, precise enough to execute the final adjustment of a taloned strike on an evasive moving target. When an eagle is circling over a river and you are standing on the bank, and you look up and see the eagle as a shape moving against the sky, and the eagle looks down and sees you, you are both looking at each other. But what each of you sees is so radically different that the concept of mutual observation becomes somewhat strained. You see a large bird at an indeterminate altitude, probably 200 or 300 feet up, probably an eagle based on the silhouette, moving on a thermal, doing whatever eagles do. The eagle sees a specific human being, individual facial features resolved, clothing texture and color registered, including UV components you cannot perceive, behavioral state being read from posture and movement and respiratory rate, and depth position precisely established. The eagle has more information about you after 2 seconds of looking than you will have about it after the entire encounter. The asymmetry is total. This perceptual asymmetry has behavioral consequences that are worth tracing through carefully, because they do not terminate simply with the observation. Eagles are not random observers of the landscape. They are problem solvers that extract behavioral information from their environment and use it to make decisions. The visual system described above did not evolve for the abstract appreciation of fine detail. It evolved in the context of predation, specifically the predation of fast, evasive, often partially concealed prey in a variety of lighting and terrain conditions. Every element of that visual system, the dual foveae, the tetrachromacy, the flicker fusion rate, the temporal resolution, has a functional role in the predatory behavioral sequence. The system, is a predator's system. It is built to find things, to assess them, to track them, and to time a strike against them with the kind of precision that determines whether the hunting attempt succeeds or fails. When this system is pointed at a human being, it is doing what it does with everything it looks at. It is assessing. The assessment is not the assessment of a threat. Bald eagles do not hunt humans. They are not equipped to kill a human adult, and they do not attempt to. The documented incidents of bald eagles injuring humans are almost entirely defensive encounters, near nest sites, situations where the eagle perceived a threat to eggs or juveniles and responded with the same defensive aggression it would direct at any large intruder in that context. The bald eagle, looking at you from across a river, is not thinking about attacking you, but it is assessing you in the specific sense that any large predator with a sophisticated perceptual system assesses novel objects in its environment. It is building a behavioral profile. It is categorizing you as a type. It is determining, through the application of a visual intelligence that operates at a resolution far beyond your own, what you are doing, whether you are moving, where you are likely to go, whether you represent a threat to it, and whether the space you occupy is a space it needs to account for in its own behavioral planning. The category into which the eagle places you is not the category you would choose for yourself. Humans tend to think of themselves as the observing subjects of wildlife encounters, the ones who look at animals, who study them, who appreciate them. The bald eagle's perceptual architecture reverses this positioning without asking permission. You are an object in the eagle's environment. You are a feature of the landscape it is navigating. You are a source of behavioral data it is processing and filing. And the information it is extracting from you about your size, your movement, your behavioral state, your potential as a disturbance to its activities is information you did not volunteer and cannot withhold. The encounter that feels to you like you are watching an eagle is, from the eagle's perspective, the eagle cataloging a large, slow, poorly camouflaged terrestrial animal of known behavioral type. This reframing of who is watching whom in a human-eagle encounter is not merely a philosophical point. It has structural implications for how we understand the behavioral ecology of eagles in human-dominated landscapes. Bald eagles in North America have been recovering from the near extinction of the mid-20th century for roughly 50 years, following the banning of DDT in 1972 and the legal protections established by the Bald Eagle Protection Act and subsequently by the Endangered Species Act. The recovery has been remarkable by any measure. The population that stood at fewer than 500 nesting pairs in the contiguous United States in the early 1960s now numbers over 300,000 individuals. This is a conservation success story without parallel in American wildlife management history, and it deserves to be understood as such. It also means that bald eagles have been present in increasingly large numbers, in increasingly close proximity to human beings for the past 5 decades, and the behavioral literature on what that close proximity has produced is genuinely interesting. Eagles in high human density areas have demonstrated a level of behavioral flexibility around human presence that researchers studying the species' recovery have been documenting with increasing attention. In urban and suburban areas with substantial eagle populations, specifically in parts of the Pacific Northwest, around Chesapeake Bay, and in river corridor habitats where eagles concentrate during salmon runs, individual eagles have been documented engaging in behaviors that imply an assessment of human activity rather than simple tolerance or avoidance of it. Eagles near fishing areas have been documented waiting for fishing activity to produce discarded or dropped fish. They have learned the behavioral pattern of fish cleaning stations, public fish releases, and charter boat fish disposal, and they time their presence to exploit the opportunity these activities create. This is not instinctive behavior. It is learned behavior that requires the individual animal to form a behavioral model of human activity, to predict when and where that activity will produce accessible food, and to position itself accordingly. The learning requires precisely the kind of high-resolution behavioral observation that the eagle's visual system makes possible. To learn that a particular fishing pier produces fish discards at the moment the boats come in and the catches are cleaned, the eagle has to observe that pattern, register the relevant behavioral cues, correlate them with the food outcome, and build a predictive model. It has to watch humans doing things and understand, at some functional level, what those things mean in terms of the outcome that interests the eagle. It has to read human behavior, and it is doing this with a visual system that is extracting more information from the observation than the humans being observed are aware they are providing. There is a population of bald eagles in southeastern Alaska and coastal British Columbia that has been studied in the context of the commercial fishing industry, and whose behavioral flexibility around human activity represents one of the most developed examples of this dynamic in the literature. These eagles have learned the specific behavioral sequence of the commercial salmon fleet in considerable detail. They know which vessels are the tenders that collect catches from smaller boats and which are the smaller boats themselves. They know the timing of offloading operations. They know the locations along the coast where fish waste is most likely to enter the water during processing. They have adjusted their roosting and foraging patterns to position themselves near areas of fishing activity during the periods when that activity is most likely to produce food. Individual birds have been observed across multiple seasons in the same positions relative to the same vessels and operations, which implies a level of individual memory for human behavioral patterns that goes substantially beyond the opportunistic exploitation of a one-time observation. The behavioral intelligence required to maintain and apply this kind of multi-season model of human activity is not the intelligence of a simple stimulus-response machine responding to salient cues in the environment. It is a more sophisticated cognitive capacity, and it is being exercised on a continuous basis in the context of watching humans. The eagles watching the fishing fleet are doing something that, if a human were doing the same thing for the same reason, we would call strategic observation. They are watching people work in order to understand the pattern and exploit the predictable opportunities it produces. The visual system that makes this possible is the same system looking at you when you stand on the bank. The same resolution, the same temporal processing, the same capacity for behavioral inference. The eagle has been doing this with humans for long enough that it may have a behavioral model of what humans in certain contexts are likely to do next, and you have no equivalent model of it. The visual capabilities described so far have been discussed primarily in terms of acuity and color, but the system has additional components that are less well known and arguably more striking in their implications. One of these is the eagle's eye structure, in terms of the mechanical properties of the eye itself. The eyes of a bald eagle are not scaled-down versions of human eyes. They are, proportionally, enormous. An eagle's eyes account for approximately 15% of the total mass of its head, compared to roughly 1% in humans. Each eye is roughly the size of a human eye in absolute terms, despite the fact that the eagle's total body mass is only 5 to 8 kilograms in the case of adults. If human eyes were proportionally as large as eagle eyes, they would be roughly the size of baseballs and would weigh approximately 2.5 pounds each. The skull of a bald eagle is essentially built around its eyes, with the rest of the skull structure arranged to accommodate and protect visual organs of extraordinary size relative to the animal's overall dimensions. The commitment of skeletal and mass resources to vision in the bald eagle is without parallel among terrestrial vertebrates of comparable size, and it reflects, as directly as anything in animal biology ever reflects anything, the degree to which visual performance is the central organizing capability of this species. The implication of this eye size for optical performance is not merely about detector density. Large eyes collect more light. More light collection means better visual performance in low light conditions, the kind of light conditions that occur at dawn and dusk, at the edges of forested habitats, on overcast days over water. The eagle's large eyes are not just more acute in bright midday light, they are considerably more acute in the conditions of intermediate light that constitute a substantial fraction of the active day of a bird that is largely diurnal, but that initiates activity early and continues it late. When you are standing on a riverbank at dawn, in the half-light before the sun clears the horizon, and the eagle is already on its perch across the water, the light conditions that are making it difficult for you to see the eagle clearly are not significantly impairing the eagle's ability to see you. The asymmetry in visual performance that exists in full daylight is actually larger in the low-light conditions of early morning and late afternoon, not smaller. The times when you feel least visible, because the light is worst, are the times when the gap between your visual capability and the eagle's is widest. The eye positioning and movement capabilities of the eagle add a further dimension to this picture. Eagle eyes, because of the way the skull is constructed to accommodate their size, are largely fixed in their orbits. An eagle cannot move its eyes in the socket the way a human can. The compensatory mechanism is head mobility. An eagle can rotate its head approximately 270 degrees and can tilt it to a variety of angles that produce an extremely wide sampling of the visual field when combined with the lateral positioning of the eyes. The total visual field of a bald eagle encompasses approximately 340 degrees of the horizontal plane, leaving only a small blind spot directly behind the head. The binocular overlap region, the zone of the visual field in which both eyes contribute to the image, is a roughly 40-degree cone in front of the eagle's head, and this is the zone in which the temporal fovea system provides the high-resolution binocular processing described earlier. But the remaining 300 degrees of the visual field, sampled monocularly by one eye or the other, are not being ignored. They are being monitored in parallel by the peripheral visual system, which in eagles retains a sensitivity to movement and coarse form detection that is substantially better than human peripheral vision across the entire range. What this means in practice is that when you are watching an eagle and the eagle appears to be looking away from you, facing a different direction, apparently attending to something else, it may nonetheless have you in continuous peripheral visual monitoring. The eagle that looks away is not looking away from you in the sense that a human looking away has removed its attention from you. It has shifted the direction of its binocular high-resolution processing away from you, but you remain in its peripheral field, which is monitoring for movement and behavioral change with a sensitivity that would detect any significant action on your part. You are never not being watched, in some sense, for as long as you are within the several hundred-degree visual field of an eagle that is aware of your presence. The behavior of bald eagles in nest defense contexts illustrates the operational expression of this visual system in a context where the stakes are high enough that the eagle's full perceptual capabilities are brought to bear on the assessment of a nearby human. Bald eagle nests, called eyries, are among the largest bird nest structures in the world. A nest that has been occupied and added to over multiple seasons can reach a diameter of 8 feet and a depth of 13 feet, weighing as much as a metric ton. These structures are positioned, almost always, in a way that provides the nesting pair with maximum visual access to the surrounding environment. The site selection is not casual. Eagles return to successful nest sites for decades, and the behavioral ecology literature on nest site fidelity shows that visual access to the surrounding landscape is one of the strongest predictors of nest site selection, stronger than proximity to food resources or distance from human development in many cases. An eagle, nesting in a tall tree above a river, is positioned so that the visual system described above can monitor the maximum possible extent of the surrounding environment. When a human approaches a nest site, the eagle's response follows a sequence that reflects both the extraordinary perceptual capability of the animal and the decision-making process it is running based on the information that perception provides. The eagle is aware of you long before you are aware that it is aware of you. At a distance of half a mile, it has registered your presence, your size, your movement direction, your pace. It has begun assessing whether your trajectory is converging on its nest site. It is running a predictive model based on your observable behavioral state and movement pattern, determining the probability that you represent a threat. This assessment is continuous. The eagle is updating it in real time as you move, incorporating new information about your behavioral state, adjusting its threat estimate based on changes in your movement and behavior. The response threshold varies by individual, by the vulnerability of the nest contents, eggs versus small chicks versus large juveniles, by the specific history of the nest site, whether humans have disturbed it before, and by the individual eagle's assessment of your specific behavioral signals. An eagle that has experienced human nest disturbance previously will have a lower response threshold for defensive behavior than a naive individual in a pristine location. An eagle whose nest contains eggs will respond at a greater distance than one whose nest contains large, nearly fledged juveniles. And an eagle that has been reading your behavioral signals for the past half mile and has registered something in your posture, your pace, the direction of your gaze, that matches its internal model of a threat, will initiate defensive behavior earlier than one whose assessment has produced a lower threat estimate. The defensive behavior itself is calibrated. Eagles do not launch into full attack mode at the first sign of any disturbance. They have a graduated response sequence that escalates through posture changes, alarm calls, and increasing agitation before reaching the aerial strike behavior that is the final stage of the sequence. Researchers studying eagle nest defense have documented that eagles with high temporal resolution visual systems, i.e., eagles generally, are reading the human's behavioral response to the graduated warning signals with the same acuity they are using to read the initial approach. An eagle, watching a person stop, look up, see the agitated bird, and begin to back away slowly, is reading a different behavioral signal from one watching a person who continues approaching without acknowledgement. The bird is processing your response to its warning at the same resolution at which it is processing everything else about you. And the behavioral decision it makes about whether to escalate or de-escalate is based partly on what it reads in your response. There is a specific class of human behavior in eagle country that the literature on eagle-human conflict documents with uncomfortable frequency, which is the behavior of adults with small children moving through known eagle nesting areas. The nest defense incidents involving bald eagles and small children are not common. They are common enough to have produced a documented record across multiple states and provinces, and the pattern within that record reveals something that is worth examining carefully. Eagles in nest defense mode that escalate to contact behavior, meaning they make physical contact with a human, are doing so almost exclusively in situations where the target of the contact is small relative to adult human size. Children under approximately 10 years of age and small adults are represented in contact incidents at a rate substantially higher than their representation in the population of people who visit eagle nesting areas. This is not primarily about the small person being more threatening to the eagle. It is about something in the behavioral signal that a small person presents that differs from the signal presented by a large adult. Eagles are prey specialists. They take a range of prey types, including waterfowl, fish, small mammals, and occasionally other birds. But the common thread running through the size class of their prey is a specific range. The largest prey taken routinely by bald eagles is a category of waterfowl, including geese and large ducks, animals in the approximately 2 to 5 kilogram range. Young children in the age range of nest defense incidents are in a size range that, from the eagle's prey assessment system, is not enormously different from a large water bird. This is not a metaphor. This is an inference about the perceptual categories that the eagle's visual system is applying when it looks at a small human child from an elevated perspective. The same visual system that is resolving fine detail and reading behavioral cues and tracking movement at double the temporal resolution of human vision is also running the image through an assessment framework that has been built by evolutionary selection on the basis of prey size, shape, movement signature, and behavioral cues. A small child viewed from above, moving and making noise, presents a set of those cues that, under conditions of defensive arousal, may be processed differently from the cues presented by a tall adult. The documented incidents are informative, and they are worth examining without the softening language that typically accompanies coverage of them. In 2012, a 4-year-old child in a park in Anchorage, Alaska, was struck by a bald eagle that had a nest in a tree at the edge of the park. The strike was from above and behind, the classic predatory strike position, and produced laceration injuries to the child's scalp. Wildlife managers investigated and concluded that the eagle was in nest defense mode and that the contact was defensive rather than predatory in intent. The conclusion is probably correct, but the distinction between a defensive strike directed at a perceived threat and a predatory strike directed at potential prey is a distinction that matters enormously to the classification of the incident in wildlife management records, and matters considerably less to the 4-year-old who was struck from above by an animal with talons capable of exerting several hundred pounds of gripping force. The injury in that case was significant, but not fatal. The visual system that produced the assessment leading to that strike was the same visual system that can detect a mouse at 2 miles. It was reading the small human being with a resolution and a capability that the small human being and the adults with her had no access to. And the assessment it produced was, whatever it was, incorrect in a specific and consequential way. There is a more recent case, from 2019, in which a child in New Jersey, approximately 6 years old, was struck by an eagle at a recreational area adjacent to a known eagle nesting territory. Again, wildlife managers classified the incident as nest defense behavior. Again, the child sustained scalp lacerations. Again, the visual assessment that preceded the attack was an assessment conducted by a system operating at a resolution and a speed that the people present had no equivalent to and no awareness of. The pattern across these incidents is consistent enough that wildlife managers in areas of high eagle density adjacent to nesting sites have been updating their guidance for visitors with children, specifically recommending that children wear hats in eagle nesting areas, that adults maintain close physical contact with children in those areas, and that groups with children avoid paths that pass within the likely nest defense radius of active eagle nests. The guidance is sensible. The thing that makes it genuinely interesting in the context of this discussion is what it implies about the eagle's visual system. The recommendation to wear hats is not arbitrary. It reflects the inference that something about the visual profile of a small, unhatted human head, its size, its shape when viewed from above, its movement, triggers a response threshold in the eagle's prey or threat assessment that a hatted head does not trigger to the same degree. This is a recommendation based on the management community's implicit understanding that what the eagle sees when it looks at a small child is not neutral, that the visual assessment being conducted produces a result that sometimes crosses a threshold, and that modifying the visual signal the child presents can shift the result of that assessment. You are being asked, implicitly, to manage how you appear to a visual system that is more acute than your own, and that is applying a categorical framework you do not have direct access to. This is not a comfortable position. It is the exact position the title of this video describes. The water hunting behavior of bald eagles provides another window into the operational sophistication of the visual system that is also the system looking at you. Eagles hunting fish face a specific and technically demanding visual problem. The surface of water is reflective. Light from the sky reflects off the surface in a way that creates glare, reducing or eliminating the ability to see through the surface to the prey below. Human eyes are subject to this problem without correction. An eagle hunting over water is also subject to it. The way the eagle's visual system deals with it is through the presence, in the eagle's eye, of a structure that does not exist in the human eye. The pecten oculi is a tissue structure present in the eyes of all birds and of some reptiles, absent in mammals, whose exact function has been debated in the literature for well over a century. The current consensus is that the pecten oculi serves multiple functions, including retinal nutrition and intraocular pressure regulation, but a substantial body of evidence points to an additional role in glare reduction. The structure, which projects from the retina into the vitreous humor of the eye, creates a self-shadowing effect on the retina that may reduce the impact of bright, reflective surfaces on visual acuity. Combined with the UV sensitivity of the eagle's tetrachromatic color system, which allows the detection of visual contrasts that are not visible in the wavelengths human eyes sample. The eagle over a river is seeing through the surface reflection in a way that human observers without polarizing lenses cannot approach. When the eagle adjusts its angle of approach over a fishing river, banking in a specific way as it passes over sections of the current, it is not behaving randomly. It is optimizing its viewing angle relative to the sun position and the surface reflection geometry to maximize the transparency of the surface to its visual system. The specific banking behavior has been documented in studies of foraging eagles and represents a behavioral expression of an optical constraint that the eagle's visual system is solving in real time. The same optical sophistication that allows this surface glare management is part of the same overall visual system that is operating when the eagle looks at you. It is not managing glare when it looks at you, because you are not a reflective surface in the relevant sense. But the underlying hardware is the same, and it has capabilities in the context of looking at you that are no less extraordinary than its capabilities in the context of looking through a river surface at a fish 4 feet below. The magnetic sensitivity that has been documented in some bird species, including raptors, and is believed to be mediated at least partly through specialized photoreceptors in the retina, adds a further dimension to the bird's perceptual system that is relevant to any comprehensive account of what an eagle sees. The cryptochrome proteins present in avian retinal photoreceptors are sensitive to the quantum mechanical effects of Earth's magnetic field on electron spin states within the molecule, producing a signal that the bird's visual system may encode as a visual overlay, a patterning of the visual field that provides magnetic field direction information as a component of the visual image itself. The evidence for this mechanism in bald eagles specifically is not as strong as in some migratory bird species, and the behavioral consequences of it in the context of an eagle looking at a stationary human being are not straightforward to characterize. But the broader point is relevant. The bald eagle may be looking at a visual world that contains information channels, including the UV channel and potentially a magnetic field overlay that simply do not exist in the human visual experience of the same environment. When the eagle is looking at you, it is looking at you in a world that has more information in it than your visual system can perceive. What you see when you look at the eagle is a subset of what the eagle sees when it looks at you, in a way that is not trivially small. Understanding the perceptual world of an animal with this kind of visual capability requires an honest acknowledgement of a conceptual limitation that is easy to state and difficult to genuinely internalize. Humans understand other animals' perceptions through analogy with human perception. We describe eagle vision as being like human vision, but better, more acute, more colorful, faster. This is a useful approximation, and it is genuinely informative as far as it goes. But it misses something that is not merely a matter of degree. The eagle's visual world is not a higher resolution, broader spectrum version of the human visual world. It is a different world, built from different information, organized by a different neural architecture, serving a different behavioral purpose. The perceptual categories that organize the eagle's visual experience of its environment, the categories of prey and non-prey, of threat and non-threat, of occupied territory and unoccupied territory, of individual conspecific and stranger, are not the categories that organize human visual experience. They are the categories that evolution produced for an animal that survives by hunting and is hunted in turn, that navigates large landscapes by vision, and that conducts its social life through visual signals at distances that would be opaque to human vision. When the eagle looks at you, it is applying these categories to your image. It is asking, in the functional sense, that a nervous system asks questions without conscious deliberation, what you are in terms that are meaningful to its behavioral repertoire. The answer it arrives at is not the answer you would arrive at if the roles were reversed. It is an answer expressed in the perceptual vocabulary